Regression is a class of supervised learning algorithms where the output variable is continuous in nature. So in continuous variables, the issue is we are not usually able to have very high performance evaluation like accuracy. Instead, we discuss about how far is the projected solution from the actual data. And that's why we have errors condition like root mean square error, which gives an idea of what is the average spread of the error in terms of what is the average distance between projected point and the actual point. And we have normalized error function like R square. So let's look at some of the popular regression techniques. One of the most important regression technique is quite old. It comes from the statistical science of curve fitting. It's called linear regression. So linear regression bases itself on the notion that any data can be fit approximated by a straight line. The basic idea is if you have a set of data points, you can approximate it with a straight line, and the idea is you feel that straight line is good enough to capture the data present in the original data. So here, the point where it touches the origin or it touches the when x equal to 0, what's called the intercept. So that is intercept. And then the parameters here are the coefficients of each of the variables. Now, when you look at fitting a straight line, you will typically have the evaluation measure as root mean square error, where you will see whatever is the original original minus corresponding y value. You will take a sum of that, then you will do a square root of that divided by n. The point is RMSE gives you a measure of how far the projected solution from the original data is by taking a square of the errors, summing them, divided by n and taking the root of that. Other approach is to look at, instead of actual mean square error, you can also look at individually what is the gap between projected and this is called the residuals. So residuals are nothing but the gap, exact gap between projected point and the actual point. So there are several reasons why we want to keep residuals to the minimum so that the net RMSE is lower. So usual idea is that usually you may have infinite number of potential candidates for M1, M2, M3, M0, etc. It can be candidate straight lines describing the original data. But the idea is you try to minimize the error function, which is RMSE. And the coefficients which give rise to the minimum error is what is chosen as the final candidate solution describing your original data, and this becomes your final model. So there is an alternative explanation to how to arrive at this by means of something called as gradient descent, in terms of how you can look at error as it proceeds with different combinations of M1, M2, M0, etc. and how this can be arrived at a minimum point in the global optimization curve, and that is what gives you the resultant so-called estimator for your linear regressor. But the same thing can also be arrived at by using what is known as maximum likelihood estimator. But the idea is both of them converge, and the basic principle is that we try to minimize the overall sum of squared errors, and that becomes the candidate linear classifier for the original input data. As we see, regression is basically the part of supervised learning where the output variable is continuous and we expect the output variable to be a continuous variable rather than a specific class. A class of contemporary to classification trees in context of classification trees in context of decision trees is regression trees. Regression trees is just like classification trees. The basic difference being that in the leaf node, instead of having one specific class, you will typically have a range of values. But the concept of the node still remains same like what you would have in the concept as in a classification tree, namely that you will have to take one variable and determine some range which will break the solution space or search space into two parts. Then at the second level you have another point of break which will then further break into two or more parts, and each branch can have a different decision point which is independent of the other. And the way this is chosen, as we discussed, is by looking at how the entropy or Gini coefficient plays out in the context of the corresponding choice of the variable on which you decide to choose. The only difference from the classical classification tree is that at the leaf node, here you will have all the data points, say between 3 to 5, 3.1, 3.2, 3.4. Similarly, here you may have a range of data points between 4.0 to maybe 5.1 to 6.5. The idea is this is something which is parameterizable in terms of the leaf node. What is the range you're looking at? You can collect multiple data points per leaf node, or you can choose, if you choose it directly as one data point, then it becomes a very large regression tree with very small decision at leaf node. But the point is, usually regression trees are carried out such that at each leaf node you have a range of values, and all the input data where output falls between these follow this path of the tree. Then, just like the classification tree, we again here can convert the path followed from the root all the way to the leaf node in form of a rule which says x1 is suppose less than 5 and x3 is less than 5.5. Output will be between 3 to 5. So that is probably an addition tree rule generated from the regression tree. So if you see, the major difference from classification tree is in the way you treat your output variable at the leaf node, and here in the leaf node you do not work on a concept of a specific class of output. Instead you work on a notion of what is called as a range of the output values which are potentially qualifying for that leaf node. So that way we have converted the problem which is usually earlier meant for classification to take care of continuous output, and the only issue is if you don't manipulate the range for leaf node properly, there is a risk of explosion of the decision tree to a very large size. If you have very granular leaf node which is saying that I want for 3.5 one node, 3.6 another node, 3.7 another node, that means you talk about a huge number of leaf nodes, and that results in a large amount of nodes in the decision tree. So instead what we typically do is we work on a range at the leaf node of the regression tree, and we let the regression tree be constructed such that we are able to have a manageable size both in terms of the depth and also in terms of overall number of nodes that it needs to carry out. So regression tree is an elegant approach to handle regression. Just like the linear regression, it works for regression, but we see that the knowledge representation as contained in regression tree is far more granular as compared to what you see in a linear regression, because we can generate a plethora of rules together forming a knowledge base rather than a simple one-liner equation which is a collection of coefficients and a linear sum. So that way regression trees are more powerful in terms of knowledge representation as compared to classical linear regression.